In this video, I'm going to go through the steps associated with conducting a bivariate regression analysis, which is relevant to the study by Corwin et al. In 2003, where they were interested in looking at using hemoglobin levels, which is related to iron in the diet, and depression levels, self-reported depression. And so the first step I need to look at here is determining whether the variables are continuous, so interval ratio type level of measurement. And hemoglobin is definitely measured on some sort of continuous scale. Obviously this is continuous. And depression is also continuous. You can see that the numbers are increasing. Higher levels of these scores on the depression scale are related to higher levels of depression. So this would be an interval, and this is probably a ratio scale, I would say. And so we've got a check mark for that. We can do the analysis. We can insert a check mark. Okay, check mark done. Our variables are continuously scored. They're definitely not nominal. They're not ordinal. They're interval ratio. So check normality and outliers for both variables. Okay, well, I've done that before many times in the textbook. Go into Explore and put HB, hemoglobin levels, and depression in the dependent list. Click on Statistics and click on Outliers and click OK and click on Plots and click Histogram. Deselect stem and leaf. Click OK. And let's see what we got here. Let's see if skew and kurtosis are elevated. Definitely not. We have hemoglobin levels with very little skew, 0.016. We want to see that less than 2.0 in absolute values, and kurtosis 0.99. And depression is also skewness more substantial there, 1.387. And so a lot different than the skewness in the hemoglobin level. So a little bit of a concern there that even though it is less than 2, it's substantially different than the other variable. And kurtosis 0.834. How about extreme values like outliers? Here's the distribution of hemoglobin levels that were reported in this study. And it looks fairly normal. Now we do have some outlier situation here with the on both sides of the distribution for the depression variable. And this is kind of typically what you'd expect to see in an analysis with depression scores, because most people don't score very high on depression. They score lowish. And so it's very positively skewed. Now it's not so bad as to be greater than 2.0, but I am concerned about this. This is very deviant from the other distribution. So this one's definitely not positively skewed, but this one is. And it does look like maybe I've got some outliers in the, I should have said outliers in the hemoglobin level, but the skewness there is so trivial that I think it's more of a reflection of the fact that there's a bit of kurtosis going on here. I actually wouldn't be concerned about these outliers. You could Winsorize them if you wanted to, as I described in a previous chapter. I would probably use bootstrapping here because the difference in the skew is too much for me between the two variables. If they were both skewed about the same thing, maybe I would carry on with a normal theory, but I'm actually going to use bootstrapping here. And bootstrapping doesn't assume any level of normality, and it doesn't assume whether there are outliers or not. So I'm giving myself a check mark there because I figured out what I need to do here. I'm actually going to use bootstrapping, and I'm going to run the bivariate regression analysis now, but with bootstrapping. So regression, if you don't have access to bootstrapping, that's fine. I'll show you what the results look like without the bootstrapping. We'll actually be able to compare them. So depression in here and hemoglobin in here. And I'm going to bootstrap this. So I want 2,000 replications, I think, is a good number for this sort of thing. Bias corrected accelerated. Click continue and click, let's see here. Options. No, I'm fine. Statistics. I could get the confidence intervals because I'm going to have to get those anyway in a subsequent step. So I'm going to say yes to that. And these are normal theory confidence intervals, by the way. So the bootstrapping is going to calculate the bootstrapping confidence intervals, and that last button I clicked is going to report the normal theory confidence intervals. So let's just let this analysis run. It might take a minute or so. Here we go. And we can see here that we've got the dependent variable, which is depression, and we've got hemoglobin levels, which are the predictor of depression. So we definitely, that's definitely the model that we're testing here, that people's iron levels in their diet produces a certain hemoglobin level, and that lower levels of hemoglobin might be related to higher levels of depression. We'll find out. Here's the model summary where you get the R value, 0.37. That is going to be the same thing as the standardized beta weight in absolute terms. So the model R is 0.37. It doesn't tell you whether it's negative or positive. And the adjusted R square, the R square is 0.138. So 13.8% of the variance in self-reported depression is accounted for by hemoglobin levels in this study, which has a sample size of, I think it's 20, how much, what do we have? 37. A sample size of 37. So not negligible. That's a pretty decent percentage, I think, for a variable. Now, adjusted R squared is the more accurate estimate in the population, so technically you should be reporting the adjusted R square. And then we have the standard error of estimate here, 7.149. Most people do not report the standard error of estimate in their results. You can ignore this table because it's redundant with other information. So here is the coefficient table which we should be looking at, and in particular the standardized beta weight in this study. And you can see that it's negative 0.372, and it's statistically significant, p equal 0.023. So this, and the unstandardized beta weight is negative 1.93. And the significance is actually accorded to both of them. There's not a separate p-value for each beta weight. They both have the same statistical significance in this table. And then we have the normal theory confidence interval here of negative 0.359 and negative 0.028. And because this confidence interval, the lower bound and the upper bound, are both in the negative territory and the point estimate's negative, we can declare statistical significance. Now, this is all based on normal theory estimation, which I've abandoned because I don't feel comfortable with the level of normality in the data. So I should be focusing on the bootstrapped coefficient, and that analysis has failed to reject the null hypothesis. Look at that. We got a p-value of 0.063, which is suggesting non-significance, but the bias-corrected accelerated approach to confidence interval estimation is suggesting statistical significance. And again, this is another example of when you get some disparity in the results and you're going to have to make a judgment call as to which ones to use. Now, I would abandon using normal theory because I don't feel comfortable about the level of difference in the skew across the variables. And arguably, the bias-corrected accelerated results are more accurate than the non-bias corrected. So this standard error that was estimated with the 2,000 replications is not as trustworthy on average in comparison to the bias-corrected accelerated. And so the bias-corrected accelerated confidence interval for the unstandardized beta weight is a lower bound negative 0.38 and an upper bound negative 0.001. It's just barely statistically significant. So I would probably rely on that value there. I'd admit my sample size isn't very big, and then I would say the results suggest the possibility of an effect. And basically what the result is saying is that for each unit increase in hemoglobin levels, there's a 0.19 decrease in self-reported depression levels. And that result is just barely statistically significant with the bias-corrected accelerated confidence interval, but it's actually not significant with this not bias-corrected result. But it is significant with the normal theory approach. But I'm going to ignore that one. So the problem here that I have here is that interpreting the unstandardized beta weight is not that informative because the scale upon which depression is scored doesn't really make a lot of sense to anyone. What does that mean to score 0.19 less on a depression scale? It's not like saying somebody earns $19 less per day, which is a very intuitive way to interpret a result. This is 0.19 decrease. For each unit increase in hemoglobin levels, there's a 0.19 decrease in self-reported depression, but I don't know what that is. What do these numbers mean? I have no idea, really. So you really should be focusing on the standardized results, and in order to get the standardized confidence intervals, you actually have to transform the data into z-scores first. So go into Analyze, Descriptives, and put your two variables into this box and click Standardized Variables, and SPSS will create two new variables that are standardized. It didn't actually happen for me. What happened there? It's trying to say variables. Well, isn't it? Oh, you know what? I clicked on bootstrapping, and you always need to deselect the bootstrapping because it's just going to carry on with you everywhere you go. So let's redo that. And here I've got Z hemoglobin and Z depression. And now I can reanalyze these data looking at the standardized beta weight, because that's the main thing I want to look at, because this is really not that interpretable with the unstandardized beta weight. And I want to get the confidence intervals. So I should point out that, yes, I do get the standardized beta weight in this result here, negative 0.372, but the confidence intervals are not there. I don't get the confidence intervals for this value here, and I want to get the confidence intervals for the standardized beta weight, because that's how I want to interpret my data. I don't want to interpret this meaningless negative 0.19. So let's go into regression and redo this analysis. And let's click on Bootstrap, redo the 2000 bias corrected, and I want to do it on the standardized variables. That's my dependent variable, and this is my independent variable. Hemoglobin, predicting depression. Yep. Click on OK. And the regression is running. We'll take a minute. Here we go. And we have confirmation. It's the last table we want to look at. Bootstrap for coefficients, negative 0.37. So that means that a 1 standard deviation increase in hemoglobin levels is associated with a 37% decrease in 37% standard deviation of a decrease in depression levels. That's pretty big. I don't know what this scale is. I don't know really what 25, 7, 3, 4, what does that mean? But I do understand that when I interpret a standardized beta weight and I say that there's a 37.2% reduction in a standard deviation decrease in depression levels for each standard deviation increase in hemoglobin levels, I think that's a pretty big deal. And we have here the confidence intervals, which are both on the negative side, negative 0.737 and negative 0.05. Both of them are on the negative side, which supports the idea that there's a statistically significant effect here. I would ignore this one because this is not bias corrected. I would trust more the bias corrected accelerated in most cases. And again, I would ignore the normal theory stuff. And again, that's because the data are normally not sufficiently normally distributed across both variables in the same way. So I've conducted the regression. I've checked the beta weight. I've interpreted it. I haven't really looked at the intercept, but because I'm interested only in the standardized beta weight, the intercept's 0. And that's going to be the case in every case. So it's not actually interesting. So let's go back to our Excel table. And we can see that I now have to look at the scatter plot for linearity. Yep, okay. Scatter plot, simple, define. And I'm going to put my, I'm going to look at the non-standardized variables because it'll be clearer that way. So I want hemoglobin in the x-axis because that's the predictor, depression in the y-axis because that's the variable that's predicted. And here's what the scatter plot looks like. It's definitely, there's a downward trend in this. We could actually get the line of best fit. So the downward trend is saying that there is a negative slope there, which means that higher levels of hemoglobin are associated with lower levels of depression. Again, this is based on a real study here. So this is interesting. I want to get rid of the attached label line there. And I'll get rid of this r squared, which is just the percentage of variance accounted for. So here's the scale. I think this is fully, this is probably, it goes down to 0. It's quite a wide range here. The scatter plot isn't depicting anything related. There's no non-linearity here. It looks like it's pretty linear, but I do admit it doesn't look beautiful. And I think in part that's because depression scores are differentially skewed. Now, so I'm confident there's not a non-linear, like I think this is okay. It's not beautiful, but I do think it's okay. I just don't know about heteroscedasticity. And I have to say I'm a little bit worried about the possibility of it. So let's actually look at the distribution of the residuals. So analyze. I need to create those residuals. I have them as, no, I don't have them. I need to create the residuals for depression. So I'm going to go back to my original data and click on Save. And I want standardized residuals. And then I'm going to create a histogram out of that. Oh, shoot, it's redoing the bootstrapping. Of course, I forget that so often. It's disturbing. Okay. So analyze regression. Let's see if it actually created it or not. It didn't. So let's redo. Let's go into regression, linear, and deselect bootstrap. I don't want the bootstrapping again, but I do want to save the standardized residuals. Click OK, and SPSS will have created a new variable, ZRE. Those are the residuals. And I want to see the distribution of that. Actually, I'm going to check to see if there are outliers. So descriptives, explore, residuals, and I've already done this, so it should be all selected. Yep, histogram, yep. Okay, so let's see what the histogram looks like, and let's see if it picks up any outliers. It's not the most beautiful residual, is it? These are obviously non-normally distributed. There are no outliers in terms of using the interquartile range rule of residual outliers, but this is not normally distributed. I mean, the skewness here is quite substantial. I could estimate skew specifically, but no, let me do it quickly. Actually, it was probably reported up there. Yes. So here's the skew, 1.26, and so that's a bit disturbing. So I don't feel comfortable with this, and I'm starting to get a feeling that there's statistically significant heteroscedasticity in these data. So I'm going to estimate it both ways. I'm going to look at the correlation between predicted values and the absolute predicted residuals, as I taught in the chapter. So let's go into regression and get the predicted values. Yep, standardized predicted. Click OK. Make sure bootstrapping isn't selected. Bane of my existence. Click OK, and there should be a new variable created, and it is. This is the predicted, standardized predicted, and the residuals. But I need to create these in absolute scores. Remember that? So I need to create an absolute variable, ZRE 1. Absolute, and ABS in parentheses standardized residual. Click OK, and I've got my standardized absolute residuals, and I'm going to use this to correlate with this, and let's see if there's a significant correlation. I have a feeling there is going to be one. There isn't. There you go. We don't have heteroscedasticity. So that, at least based on this test. So now let's back that up with the co-anchor test, just to be extra thorough. And I want to use the HDB variable as the explanatory variable and depression as the outcome variable. You don't need to use the standardized scores for this analysis. For the co-anchor test, use your raw scores. And it's not significant. So there you go. Co-anchor p-value 0.768 because that's greater than 0.05. I have not rejected the null hypothesis. The correlation approach supports the idea that there is not heterogeneity in the data. So I don't have to estimate corrected standard errors. So I've checked the distribution for residuals and normality. It's definitely non-normal, but then the original data were to some degree as well. I did bootstrapping, so I'm okay. I'm not worried about the fact that there's non-normality in the data or in the residuals because I did bootstrapping. I've checked the assumption of homogeneity, of homoscedasticity, and it was satisfied. Therefore, I do not have to calculate the corrected standard errors. I don't actually have to do this step. So, summary. I would argue that there is, based on this sample, which is not a big sample size of 37, I would say there is a just barely statistically significant effect between hemoglobin levels and depression. And where do I have my standardized effects? Here we go. These are the standardized, where I did the bootstrapping on the standardized variables. It's negative 0.37. So a 1 standard deviation increase in hemoglobin levels is associated with a 37.2% decrease of a standard deviation in self-reported depression levels. And that is statistically significant with 95% confidence intervals bias corrected accelerated both on the negative side. Negative 0.73, so the effect is as large as 73% of a standard deviation or as little as 1.5% of a standard deviation decrease. So really we feel confident that we can say there's probably an effect, but just how big the effect is, it's such a wide range, we don't know. We'd encourage people to do more research, for sure, given how important this sort of research is.